Greetings, we are going to study about the serial formation of water. Werner was the first scientist to propose the correct structure of formation. For that, he got the Nobel Prize in Chemistry in proposing the tidal configuration of transition metal complexes. Tidal complexes. The transition metal is linked to six ligands. They are of a geometry that is which the six ligands are placed at the four, six corners of an octahedron. He once what was mainly the appeared and characters main cooperation. A very commonly observed complex as this as a complex oxygen chloride of cobalt. The structure from the chemical reactions and other studies was found to be like this: COCl3.6 but the nature of the stone was not exactly known. It was Werner who proposed that the structure of this compound is like this, in which C cobalt, metal, and the NH3, 6 NH3 moieties are included in a square bracket, and CH remains are drawn outside the bracket. So from to arrive on this kind of structure, what he did was he did some reactions, so precipitation reaction of these complexes, many complexes that are prepared with complex with excess of silver nitrate solution. So when excess of silver nitrate is added in cold to the complex, ionizable chloride ions, chloride ions that can leave the complex as Cl minus can be precipitated as silver chloride. And this is a standard precipitation reaction, and from the precipitate we can find out how many Cl minus ions are free to move in this complex. When one mole of this complex, yellow colored COCl3 is reacted with excess of silver nitrate, it gave 3 moles of silver chloride precipitate. That means in that complex, 3 Cl minus ions are there that are not tightly bound, that are ionizable. And for the purple colored COCl3 and S3, when treated with silver nitrate and cold, gave 2 moles of silver chloride. That means the complex has 2 Cl minus ions that are ionizable. Similarly, when the green color COCl3 and H3 as well as COCl3 and H3, these are two complexes, differently colored two complexes, which are categorized as isomers. We have studied about cis-trans isomers, isomers. So these complexes, when treated with silver nitrate, each give 1 molecular edge of AgCl precipitate. That means for this complexes have 1 Cl minus as ionizer. And also did some conductivity studies. Conductivity measures the ions present in a solution. When a compound is dissolved in a solution, the ions present will determine the conductivity, the electrical conductivity of that solution. And then nowadays the first solution, the yellow colored solution, yellow colored complex, showed that there are 3 Cl minus ions ionizable. So it is evident from the conductivity values also. It's 1:3 electrolyte from the purple. For the purple colored complex, structure is like this: COCl NH3 5 times, and 2 plus is the charge of the whole complex part, and to counteract, 2 Cl minus ions are there for the electrical neutrality, and this Cl minus are free to move in the solution. So this is a 1:2 electrolyte. For the other two, structure is like this: COCl2 NH3 4 times, Cl minus ions outside the square bracket. Shows that 1:1 electrolyte. So from these studies, we propose that the structure is like this. Some particles, some groups or anions are inside the square bracket that is tightly bounded to the coordination complex. Here in the case, all the 6 NH3s are inside the square bracket and 3 Cl minus are there outside the bracket for the electrical neutrality. Here the case of, here in this case, 1 chloride ion and 5 NH3s are the inside the bracket, that means they are tightly bound to the cobalt transition metal. So from these studies, we propose that complex have such a structure in which the metal is directly linked to the ligand and it is inside a square bracket. That means they are not ionizable, they are very tightly bound. And to counter this, to maintain electrical neutrality of this whole thing, certain groups can be or cannot be present in the um, complex bond. So from these observations, Werner proposed that a transition metal will have two valences in a coordination complex, primary valence as well as secondary valence. For example, cobalt here has a, it's not a transition metal, it's an inorganic compound. It's a chloride of cobalt. It's a simple salt. So here the cobalt has a primary valence of +2. Platinum here has a primary valence of +2. Chromium here has a primary valence of +3. So this valence is there for all the metals. When these metals are becoming transition metal complexes, what they form is that they have two kinds of valences. Here the cobalt has a primary valence of +3, that is satisfied by these chloride ions. Other than that, it has a secondary valency of +6. Secondary valency of 6. That is satisfied by this ligands. So, from these old calculations, we have proposed few postulates for the structure of coordination. So, these coordination compounds metal show two types of valences, primary and secondary. The primary valences are normally ionizable. So, that is why the negative ends. In this case, here, this complex. Primary valence is +3, that is satisfied by the negative ions. Secondary valence is non-ionizable. This cannot be made. They are not ionizable. Separating this into cobalt and NH3 is not possible. Non-ions is satisfied with neutral molecules or negative ions. It can be neutral molecule or negative ions. For example, so here ammonia here is neutral. This is a platinum transition metal complex where Cl minus is a ligand that is having a negative charge. The secondary valence is equal to the coordination and it's fixed. So secondary valence is secondary valence is also called coordination number, and for every metal that is a fixed coordination number. So some secondary metal have characteristics which are corresponding to different coordination numbers. So they are not coming and attaching in a way that they want to. This a spatial orientation is to be maintained for this and coordination entity and counterions together is known as a coordination polyhedra. Coordination entity means this part, complex part, and counterions means this. Whatever the anions are there to counter. Many types of geometries are there for coordination complexes. For example, octahedral, tetrahedral, square planar. This complex have an octahedral geometry. Here, cobalt is attached to 6 NH3 groups, and the 6 NH3s are at the corners of it. This way only the terrestrial groups can go and attach the cobalt. Cobalt has a +3, that means there are Cl, 3 Cl ions. And this there's another geometry, tetrahedral geometry. Example for such complex is nickel carbonate. Structures like this, nickel is here, cobalts are carbonyl groups are attached to the Components of a tetrahedron. Then there is lemma geometries, that is for this complex by PtCl4 2 minus. Here, this Cl minus are attached to four corners of a square that is in the plane of the flat. So the type of spatial arrangements and the number of groups attached will be specific for each metal. So we'll see some examples for this. For example, for the first complex PdCl2 4 NH2. Number of moles of PdCl4 are precipitated by mole of the compound is. That means there are two Cl. That means there are two Cl minus ions present. So all this two is outside the polyhedron. So the secondary valency of this compound will be 4. And for the second one, like this one, it's also the 2 moles of silver chloride is precipitated. That means this is outside the box, and the secondary valence is 6. For this one, PtCl4 2 HCl, the number of silver chloride moles is 0. That means there are no free ionizable chloride in the structure. So the structure will be like PtCl4 2 H2O. Do it twice, all in the coordination state. So the secondary valences will be 6, 2, and 4, 6. For this compound, COCl3 formation, number of silver chloride, number of moles of silver chloride precipitate is 1. That means in the coordination sphere, there will be CO, Cl2, and NH3, 4 times, and 1 Cl is outside. That means the secondary valence is 2 plus 4, 6. For this, PtCl2, 2 NH. Number of silver chloride precipitate, number of moles of silver chloride precipitate is 0. Therefore, structure will be like PtCl2, NH3 twice. No counterbalance. So this secondary valence will be 4. So this is how we are calculating secondary valences of every transition metal. This is nickel. Substance. There's another class of compounds, double salts. Double salts are for general formula like this. For example, carnalite, more salt, potassium, these are all double salt. These are mixtures of different compounds. For example, carnalite is a mixture of calcium chloride, magnesium chloride, and water. It's hydrate chlorides of calcium, potassium, and magnesium. So then these dissolved in water. What happens when they are made a solution? You will get all the ions. You will get K plus. Carnalite in the case of K plus, Cl minus, Mg2 plus, 2Cl. All this can be ionized. So that is the clarity of doubles. All doubles when mixed dissolve, they are ionized. They are completely ionizable. So these are completely ionizable. But coordination complexes, when this is dissolved in solution, how they are going to is they are going to ionize as 4K plus Fe Cl 6 O minus. So ionization of Fe and Cl is not done for potassium ferricyanide. So somebody says your table salt has potassium ferricyanide added to it. Cyanide is there. You should not drink. It's a poison. You should not take the table salt. Don't be with them because it is a complex. It's a potassium ferricyanide. Claiming this cyanide ions is not possible for us. Possible under any circumstances. Potassium ferricyanide is different from potassium cyanide or originals. So, with this, we are coming to the end of the short topic of honesty and coordination hormones. We will see in the next topic. Thank you for watching.